I want to spend the last several minutes talking about another kind of structure because what you're going to do for your next homework assignment that I think is now appearing on the website, you're going to use arrays and linked lists to implement a structure called a priority queue. I mean, basically, I want to make you use the stuff we learned about arrays and linked lists. I want to make you build something with it. And what you're going to build with them is a priority queue. So let me tell you what a priority queue is, so you'll know what's going on. And of course, if you go to the Yeah Hours session this week, you can learn more. There's a lot of problems that come up where you're involving urgency or priority or something like that, like a printer that's shared among a lot of people. Say, by the way, AV, can we get the lights a little lower? I feel like the projector is kind of hard to read in the top left corner. If you dim me a little bit, that would be awesome. So, great. I think, there you go. Thank you. That's perfect. A lot of times you have priority or urgency to different tasks that you need to do. So imagine you have a shared printer. All the faculty and students print to the same printer. In general, it's first come, first serve, right? If I push the print button before you, my papers come out before your papers. But sometimes it queues up because there's a lot of jobs coming and the printer is slower than the jobs. And in general, it's first come, first serve in that queue. But maybe you have a setting so the faculty can cut in front of the students, or people who pay extra can jump in line or something like that. So they have a higher priority. Another good example is an emergency room. If you come in with a cold or a bloody nose, that's fine. They'll be happy to serve you. But if somebody comes in with like their head hanging off and their head broke off their body, you probably want to help them. Well, I don't know. Somebody with a more serious injury, you want to tend to them first. They have a higher priority than you. So if you were thinking of this like a computer scientist, you'd say, oh, I've got a list, I've got a data structure, maybe a queue of all the tasks I need to work on. It's basically a queue where you add at the back of the line and you dequeue at the front of the line. But really what I want is I want to be able to add them, but then I want to remove the most urgent one in the line at any given moment. Give me the most urgent patient, I'll process them. And a data structure that would do this well is called a priority queue. So this is a new abstract data type I'm only going to show you a little bit about. But the operations are enqueue, but you enqueue an element with a priority, with an urgency level. And the convention we're going to use here is that a smaller number is more urgent. Like priority 1 is first priority. That's more urgent than priority 2. OK? And now somehow it's got all that stuff stored in there. I drew a big blob. Who knows what it's doing with all that stuff. And then later, if you say, OK, DQ, it's going to pop out the one that has the most urgent priority first. If with a priority of 2 comes out. And then the next time you ask for something, it'll be one of the ones of priority 3. And later, it'll be the ones of priority 4, and so on. OK? That's what this thing does. There is such a thing in the Stanford libraries. There's a class called priority queues. So somebody already wrote one of these somewhere. And these are the operations that it has. Enqueue, dequeue, peek. You can peek at what the next piece of data will be, and you can peek at what its priority would be. Sorry, my slide looks like my slide cut off funny here. But there's a lot of the common stuff. Is it empty? What's the size? You can print it. You can clear the elements out. So here's an example of me creating and using a priority queue. I make a priority queue of strings. I add myself with priority 5. I add Eric Roberts with a higher priority. He's more important than me. He makes more money than I do. So that's one of the structures you can already use in the system. Now, I've got an example program that uses these, and I'm not going to write it because I want to make sure we have enough time to talk about what I want to talk about. But you could read in some data, store it in a priority queue, and pull it out. And what this program is doing, you can look at this later on the website. I'm reading in data about section leaders and how long they've been working in the program. And I insert them with a priority that's related to how long they've been, or when they started working as a section leader. And then when I dequeue them, it pops them out in increasing seniority levels. So like, it stores when they started working as the priority. So people who started working earlier, those are smaller numbers. Therefore, those are considered to be more urgent priorities. Therefore, the earlier you got hired, the earlier you pop out of this queue. So if I were letting people pick what kind of pizza they want, and I let the more elder section leaders pick first, this structure will pop them out in that order, basically. OK? You can look at this later. Now, OK. The question that this raises is how would you, if the Stanford library didn't come with this, how would you build this thing? What's it doing internally in order to be able to support this sort of a behavior? How does it work? Well, there's a couple of ways you could do it. You could build it using an array or a vector or something like that. And as you have new data that comes in, you could just add it to the end, kind of like we did with our array list. Just put it at the end, increase size by 1. And so I add X with priority 5. I add B with priority 4. Just put them in there. OK. Well, tell me, just as an implementer, if I need to be able to add things and then pull things out that have the highest priority, how long does it take for me to add something if I use this kind of a representation? Big O of what? Big O of 1, it doesn't take very long. I just put it at the end. It takes a constant amount of time. Because I'm not storing them in any particular order, other than order of insertion. Now, what if I want to pull out, remove, and return the one that has the most urgent priority? How do I do that? How long does that take? It takes n, like I have to loop over them all and look at them all and find the one that has the lowest priority. And it's not sorted, so it could be anywhere. Find it, pull that one out, shift people over, right? I have to do that kind of stuff to find it and remove the most urgent one. Yeah, what about peeking? I just want to peek at which one has the most urgent priority. I don't want to remove it. That's also slow. I have to look at everybody to find which one that is, right? Did you have a question? Yeah. Could you use a map for this? Sure, you'd have to keep a map from priorities to elements or elements to priorities. Yeah, that's definitely an implementation strategy that you could use. I'm not going to show slides on that, but there's about 100 different ways you could implement this thing. I was just showing kind of an unsorted array as one possible implementation, partly because you're going to do some of this sort of stuff on the homework assignment. I won't make you do one as a map on the homework, but if you want to do that as an extra feature, you could. So that's one way you could do it. Another way would be you could make it an array or a vector, but you could sort it. That might work, right? Maybe that seems better to you because I don't have to look around certain times, right? If I'm adding a new piece of data to this, how long does it take? The old way, I just put it at the end because I wasn't really organizing it at all, right? But now if I want to keep them sorted by priority from most to least urgent, now I got to find the right place to put the thing, right? Got to look around, find the spot, slide people over, and put it in the slot. That takes a long time. Might take n time. If I'm removing the most urgent element and returning it, how long does that take? That's a lot faster now. That takes a constant amount of time, big O of 1, because the most urgent element is now always the one that's at the front, right? Of course, when I remove it and return it, I still have to shift everybody over, so that part is slow. Oops. So if I'm peeking at it, that's fast. But if I'm actually removing it, the shifting makes that become slow. So you have to remember, the whole operation includes all those things, right? OK, anyway, so that implementation has some pros and some cons as well. You could do a linked list. You could store these things as a linked list. Now, the boxes look a little different on my picture here. But one thing I want you to understand, the linked list that we wrote, you had an int for the data and a pointer for the next. But the data could be anything. You could even have 5 different fields of data. Data number 1, string, data number 2, double, data number 3. You could declare as many data variables in your node as you want. And then you have one pointer to the next one. So this would be an example where I have 2 pieces of data in each node, the value as a string and the priority as an int or a double or something. So I could store the nodes as a linked list. You could enqueue by adding to the front instead of to the end, because it's slow to go all the way to the end. So now it's unordered. And it has some similar pros and cons to the unsorted array or vector, where if you want to find the most urgent one, you have to loop around and look for it, right? But it's faster to add things in. And similarly, if you made a sorted linked list, you could also have some improvements in speed. In particular, if you want to peek at or remove the most urgent element, it's right there at the front. So that's really fast. And there's no shifting anymore, so the removal of the most urgent element is pretty fast here, right? But inserting, you have to loop forward and find the right place to put it and manipulate the nodes to put it into that slot, right? On your assignment, I want you to implement this one. And I want you to implement the first one, the not sorted array, and the sorted linked list. Those are 2 things I will make you do. Is I will make you write a priority queue that adds and removes things with internal structure to match those 2. Okay? And then there's a third one. The third one is the fun one. For some definition of the word fun. The third one is called a heap. And I will introduce this strategy, but really the details of this will be things that you will see when you read the assignment spec. And if you potentially go to the hours, this is how you will truly come to understand this structure in detail. A heap is like an array that is sorted in a particular order. And I want to describe how it works as following. We're going to think of every element as having parents and children. It's just a concept, just a way of thinking about it for a second. Pretend that index 0 is empty. Just leave it blank. Index number 1 stores an element. We're going to call it the root or the parent of the whole set of data. And every index has 2 children. And their indexes are double the index and double the index plus 1. So the children of index 1 are 2 and 3. The children of index 4 are 8 and 9. Children of index 212 or 424 and 425. You know, whatever. It's double yourself and double yourself plus 1. Those are your 2 children. Okay? And the reason we're going to talk about things in that way is we're going to keep this thing ordered, sorted in a particular way. We're going to keep it sorted so that parents always store things that are more urgent than their children. So what does that mean? Let me try to explain. There's some clever little algorithm tricks here that lead to a really interesting result. If you're going to add something to a heap, to this kind of an array, what you do is, first you put it at the end. So I just added k with priority 1, but 1 is a very urgent priority. And the idea is, things that are urgent should be a little bit earlier. Parents should be more urgent than their children, this kind of thing. So what you do is you repeatedly compare the new thing that you added to its parent. And if they are not in the right ordering with each other, you swap them. So the parent of k here, element 7, would be what? Do you know? Which index is the parent of 7? It's 7 over 2, but you round down because it's integer division. So that's 3. So I compare 7 with 3, and I say, hey, the parent should be the more urgent of the 2. And because that's not true, the b with a priority of 4 is less urgent, I swap them. I just swap. I don't shift, I swap. Okay? So now the k goes to index 3, and I repeat the comparison with the new parent of k. The parent of 3 is 1, so I do the same comparison again. I keep doing it until I find that I'm in the right place, and that's when I stop. So in this example, k swaps up from 7 to 3, and since it's still out of order at 3, it swaps up again from 3 to 1. The most you can ever swap up is all the way to 1 to the start. But after you finish doing this, you have maintained this ordering again that I said was important. Now this all might seem a little abstract. Why do I care about this ordering so much? Why do I want this order? Well, let's think about it for a second. Remember what we're supposed to do? We're supposed to be able to add things, and we're supposed to be able to remove the most urgent one, right? Those are the 2 things we really need to be able to do, and hopefully do them efficiently. So adding that thing, that's one operation we needed to support. This looks complicated. If I add, I have to swap, I have to jump around. How long do you think it'll take for me to jump this thing around into the right place? Any ideas? It looks like I'm jumping pretty far up the array, so is it O of n time? It's related to the logarithm of n, because every time you jump, you're jumping by half of the distance. So divided by 2, divided by 2, divided by 2. If you're repeatedly dividing by 2, that's the log base 2 of n. So this doesn't take n time, it takes log of n time, which is actually not very slow. So that's how you add things. They bubble up, we say, to the right place. When you want to remove something, before we remove, let's talk about peeking for a second. If you just want to look at, without changing, without removing, you want to look at the one that's the most urgent in the heap. Where is it? It's always the first one. It's always the one at index 1. As long as you're implementing the adding behavior properly, then the one at index 1 is always the most urgent one. That's always the one that should come out when you want to remove or when you want to peek. So that should be fast. Well, okay, so let's talk about removing. Removing is, okay, thanks, I want the k out, give me the k, but now that I'm done with that, I want to make sure the rest of the data is still intact in the right order. So you might imagine maybe I shift everybody over or something, but first of all, that would be a little slow. Second of all, there's a more clever way of doing it. So yes, we do delete the k here. What we do to fill up this hole is we grab the last element, just grab them, move them up to the start, move them up to index 1, but now they might be out of order. So we do the opposite of what we did on the previous slide, and we bubble them down. As long as they're too unurgent, we swap them with their child. So here we we swapped up the y with the 6, and now we compare it to its children, 2 and 3, and we pick the one that's the more urgent of the 2 children and swap it up. And you repeatedly move the urgent children up and the less urgent parent down until it's put into the right place. Yeah?
Why? Why do that instead of just? I guess SSE. I was going to say why do that instead of just swapping the things that are currently at indexes 2 and 3 if 3 is higher priority than 2.
Well,
but that disrupts. I see that.
The way I would think of it is we remove the one at index 1, and so now there's like a hole there. We need to fill the hole with something. So we could grab the one from 2 or from 3 or whatever, and maybe that is what's going to end up in that hole at some point. But you don't want to get into a situation where you have to slide the whole array over by 1. That really eats your runtime because every single element, n-1 of them, has to be moved. So you don't really want to do that. What you'd rather do is just move somebody up and then bubble them down a little bit until they're back into place. That's more of a logarithmic runtime, just like the adding cost.